Well, this video screencast includes some notes on the topic of heating matter for the fifth day of the matter unit in Physics 106. So to start out, you'll want to turn to your workbook on page 32. There's a question about what is the difference between heat and temperature. So I'd encourage you to, pause the video as you need to write down some of the notes, but heat is defined as a form of energy called thermal energy, and we'll talk more about energy when we get into the motion unit. But really this has to do with the vibration of atoms and molecules in an object. So if something has more heat, there will be more energy and more vibrations of those atoms and molecules. So temperature is a quantity of how warm or cold something is. So we measure temperature oftentimes using a thermometer in degrees Fahrenheit, Celsius, or Kelvin. And so for example, you can see on this scale, this is comparing the centigrade or Celsius scale to the Fahrenheit scale, and the freezing point of water is 0 degrees Celsius but 32 degrees Fahrenheit. And the boiling point of water is at 100 degrees Celsius or 212 Fahrenheit. So if you travel to a different country that uses a Celsius temperature, oftentimes in the summer it'll be somewhere between 20 and 30, corresponding to temperatures in the 70s and 80s. So maybe you've had some experience with that before. Alright, so what happens when you add heat to matter? Well, what you're really doing is giving it more energy, so the atoms or molecules in that object start vibrating faster, and then they spread farther apart from each other. So this is a depiction of what's going on. If you have a colder object, these lines indicate how those particles are vibrating. As you add heat, they start to vibrate a little bit more and more, so that they actually need more space and start to spread out from each other. We call this process thermal expansion. Water is a little bit unusual. It actually expands when it freezes. That's why ice floats on top of water, and that has to do with its crystal structure. But for most other objects, they will expand when you heat them. So some examples or applications of this, maybe you've seen like on bridges and roadways, sometimes they have these things called expansion joints to allow for the road to expand or contract in different temperatures. And also we saw something like this when we did the stations activity on the first day of class. We saw the water level in the tube rise up when you put the flask in warmer water. And when we're in class, you'll take a look at a question about how a thermometer works on page 33. So when there's a temperature difference between two different objects, heat is always going to be transferred from the warmer object to the cooler object. And that's what's shown in this picture. There's no such thing as cold that can be transferred from other objects, but you'll often hear people say things like that, like close the door, you're letting all the cold air in or all the cold air out, or close the refrigerator, you're letting the cold out. But we're always going to talk about the transfer of heat, not cold. And we'll see this in the question on ice cold lemonade on page 32 when we talk about that in class. So there are different ways that heat can be transferred between objects. So the main three ways that we'll talk about are conduction, convection, and radiation. So conduction on page 33 is when thermal energy is transferred between physical contact. So that means that the objects are touching. And what's going on there is the atoms and molecules of the warmer object are vibrating, and they start to collide with the neighboring molecules, which are cooler and not as energetic. And so then they start to make those vibrate, and that's that transport of heat from contact. And that's what this picture is trying to show too. If this one is which has heat, it starts to vibrate and transfer some of those vibrations to the atoms and molecules around it. So some examples would be like if you're holding some ice in your hand, some of the heat from your hand, the vibrations of the particles in your hand are going to transfer some of that energy into the ice, and it may start to melt in your hand. Cooking pans, often there's some kind of element or something that's heating up on the stovetop, and then that contact with the pan is transferring some of that heat energy by physical contact with the pan, and then the pan is going to then transfer heat to the objects that are cooking in the pan, such as this grilled cheese sandwich. So another process is called convection. Convection is when you have heat transfer by the movement of a fluid molecule, and so fluids could include liquids or gases, things like air or water. What happens is that when you heat up a fluid, those particles are vibrating faster, they start to spread out from each other, and that makes it less dense. And so from what we know with floating and sinking, that something that's less dense is going to rise up or float in something that's more dense. So typically this applies to liquids and gases. For example, if you're heating water in a pot on a stovetop, what's going to happen is that from convection, the water down here is going to get heated and it's going to rise up because it's less dense, and then cooler water is going to sink down, and you get what are called convective currents inside that pot just from the movement of the fluid. Convection ovens kind of operate in this idea with air. And if you're heating a building, oftentimes the radiator, you will have some heat up the air particles around it, and then those will rise up. So if you live in the top floor of an apartment building or something like that, it's oftentimes warmer than in the lower floors, and cooler air will sink, so you get this convection going on there too. A hot air balloon often will have a flame or something like that to heat up some of the air, and that makes it warmer and less dense than the surrounding air, and that's why it'll float. And this can also help to explain breezes, and you'll see this in these pictures in the lecture notes too, but with during the daytime, you'll often get a breeze coming from the sea if you're close to an ocean or something like that, and that has to do with the way that the warmer air above the sand or the shore is going to rise up, and then when it goes over the water, it's going to cool down and sink, and so you get this convection here. But during nighttime, the opposite effect happens. So the sand cools down pretty quickly, and so the air above the sand sinks, whereas you get some breeze coming from the land to the water, and the warmer air here will rise up. Alright, so the third way is radiation. So that has to do with heat being transferred by electromagnetic waves. And we'll talk more about electromagnetic waves in the spectrum when we get to light and color. This has to do with infrared from some kind of emitting source. So typically something like the sun, which is emitting radiation or heat energy. Fire, you can feel warm when you're close to a fire. And also those incandescent light bulbs that have a filament in them. One of the reasons they're not very energy efficient is they give off so much heat. Alright, so we'll do a demonstration in class where we place some heat lamps or light bulbs on top of sand and on top of water, and we'll look at how the temperature changes. And what we should see is that the temperature of the sand is going to rise much more quickly than the temperature of water. And you've probably noticed this if you ever go to a beach on a sunny day. The sand is a lot hotter than the water is, and that has to do with an idea called specific heat capacity. So on page 34 in your workbook, you'll want to define specific heat capacity as the amount of heat that's required to raise a temperature of a substance, maybe a kilogram of that substance or a gram of that substance, by 1 degree. So water is a substance that has a very high specific heat capacity, and we saw that in that demonstration too, that it takes a lot of heat to change the temperature of water. So that means it has a high specific heat capacity, whereas with sand it doesn't take as much heat in order to change the temperature. Actually, this works out really well for animals that live underwater because there aren't these really big temperature swings. It takes a lot of heat to change that temperature, so it's often much cooler in the water. Another application is that when you're cooking on the stovetop, you're most likely not going to use a metal cooking spoon to stir things because it would get really, really hot quickly. So a lot of metals have a low heat capacity. It doesn't take very much heat to change the temperature of it. So you'll oftentimes see cooking spoons that are made out of wood or out of plastic, or maybe they have a plastic handle. Alright, so there are a couple more questions on page 36 about heating matter. So this one has to do with, why do we wear mittens, hats, and gloves during winter time? Well, these materials are poor conductors of heat, so that means that they do not transfer heat very easily. So they slow down the transfer of heat energy that you're giving off from your body, so that it's not as easily transferred to the surrounding environment. So it's really keeping that heat close to your body, not transferring it out to the environment. And this next question has to do with, if you step on a tile floor, it feels colder than if you step on a rug or a piece of carpet. But actually, they're at the same temperature, the temperature of the room. So this can be explained in the way that a tile is a better conductor of heat than carpet. So when you step on tile or wood floor or something like that, the heat from your foot is transferred to the floor by conduction really, really quickly. So then it leaves your foot feeling colder because it has transferred some of its heat away. Whereas on carpet, it doesn't really transfer very much heat to the carpet, or it's a much slower process so that your foot stays warmer. All right, so in class, there's going to be a whole bunch of questions that we look at together. So we'll be taking a look at some of these applications of these ideas with heat. We'll also be doing some brainstorming about changes of physical state, or the different phase changes that can also take place when you heat matter. And we'll look at a couple of questions related to that, turning the dial and some evaporation from wet jeans. All right, so we'll see you at class.